Morning or good afternoon. I've chosen to do number 6 on the final exam. Already from the graphs, we can determine a few knowns and unknowns. Just by looking at the graph, you can see that the overall shape of the wave is different for both history graph and snapshot graph. As you can see, the history graph looks like a reflection of the snapshot graph. We already know that when we convert a snapshot to a history, for a wave moving to the left, it is the same shape, but when moving to the right, it is the mirrored version of the snapshot graph. So we already know that since it's the mirrored version, that the histograph is a mirrored version of a snapshot graph, we know that the wave is moving right. And as for our unknowns, it is the time and our snapshot graph, and so far that's all that we have. Our only known is that it's moving to the right and that we don't know the time for our snapshot graph. Now for this problem, I will be doing things a lot differently, mainly because we have to solve for B. Actually, we have to solve for B before we start solving for A. So for this part, I will actually start solving for B instead, because you will need that answer in order to solve part A. So for part B, it is asking us what is the velocity of the wave pulse. And a hint given is that velocity also includes direction. A pulse, by definition, is a wave caused by a single disturbance that moves through a medium. The pulse has a sinusoidal pattern all throughout the graphs with a constant wave speed. The question at hand is asking out what is the wave speed. Before solving, we have to use the formula, and in this case, it is V equals lambda times frequency. Lambda, or wavelength, is the distance of one crest to another, and frequency is the number of times the pattern repeats itself, and altogether gives us the wave speed, the distance traveled by a given point of the wave in a certain interval of time. To find wavelength, we look at our snapshot, because a snapshot graph is a wave's displacement and a function of position. Our wavelength will be delta x, which means final position minus initial position. So we see from the snapshot graph that our final position is at 10 and our initial position is at 1. And what I mean by initial and final position, I mean that's when the pattern starts moving. It's not actually from this part and up to here. It's when the wave forms. So it starts forming at 1 and then ends up forming at 10. So we will get our final position 10 and our initial position 1, which gives us 9 meters. Now we can find frequency by finding the period. And to find it, we look at the history graph, because history graph shows a wave's displacement as a function of time. We do the same to the previous one and take the final time minus the initial time. So we get delta t, which is final time, minus initial time. So our final time is at 5, and our initial time is at 2. So we get delta t equals 5 minus 2, which is 3 seconds. So we all plug that in back into the formula, which we get V equals 9 times, oh, sorry, I made a mistake. Actually, this will be our period. And to find frequency from our period, it's 1 over our period. So we will get our frequency is 1 over 3. So then 9 times 1 over 3, which equals 3 meters per second. And given from the hint, it said don't forget that velocity includes direction. We know that since the wave moves right, it means that the graph is moving at a positive x direction. This would also mean that we get a positive 3 meters per second as our velocity. Now moving on from part A. Part A is asking us that the histograph shows x equals 3 meters. So we solve that part right here, x equals 3 meters. And it says that what time is the snapshot graph shown for. And to do this, we have to figure out what formula to use. We're looking at the overall time in the snapshot graph and not just one instance. We know from a previous question that the velocity is positive 3 meters per second, and that the question gives us that the overall histograph is at x equals 3 meters. To find the time of that one complete snapshot graph, we will use the formula v equals delta x over delta t. So we know that we're not solving for velocity, we're actually solving for time. So we just have to rearrange it. And we get delta t times v equals delta x. We get delta d by itself by dividing by v. So our formula now is delta t equals delta x over v. Now we just plug everything together. We put delta x, which is final minus initial, and we know that since it's saying x equals 3 meters, it's actually the whole entire graph is, for the whole entire one cycle is x equals 3 meters. It's not at one instance, so that's why we have our final would be 3 and our initial would be at 0. And then our velocity from above is 3 meters per second. And so we get delta t equals 1 second. We can even check it out. We can check out our answer by plugging it in. Let's say delta x equals v times delta t. We could plug v in, we get 3, and delta t 1. And that gives us our delta x, which is 3, which is correct. And then for part C is asking what is the maximum y velocity of a particle on the string along which the wave pulse is traveling. Now we know the original displacement formula at the y direction is dxt equals a sine kx minus omega t plus the phase constant. But the question is asking for velocity. So to turn this original formula into velocity, we have to take the derivative. And the derivative of that would be by equals dy over dt equals negative omega a cosine kx minus omega t plus the phase constant. And this is the formula for velocity of any point on a string. But you see here, a particle's maximum velocity is at 0 displacement. So the formula then becomes Vy max equals omega a. The maximum velocity of the y direction that happens to the string at point 0. maximum velocity, y direction at point 0. So to find omega, we use the formula 2 pi times frequency. Or in this case, since we already know that the frequency right here is 1 over 3, we will put 2 pi times 1 over 3 or 2 pi over 3. And then the A basically means our amplitude. And our amplitude is the maximum extent of an oscillation. So this right here is the maximum. And then this right here would also be it. So our maximum is at positive 2. Oops, sorry. So then our amplitude is at 2. So then our Vy max is equal to 2 pi over 3 times 2 or 4 pi over 3. We could also change it to 4.2 radians.